Hello, everyone. Welcome to the next lecture on deep generative models. Unfortunately, we had the issue that I don't know why, but the um, teaching station could not record session on the last Tuesday, and like the last lecture we had, which was on Wasserstein GAN. This is the reason that I'm recording this right now. So this is offline recording after the lecture, but hopefully it doesn't happen again. I mean, this is also a reason for those who are not participating in the lectures in person to try attending the lectures if that happens more often in future. Where we ended last time was we ended up discussing what is GAN, and we talked what is vanilla GAN. So vanilla GAN had a very basic idea. We wanted to somehow develop a kind of flow-based model, basically starting from a Gaussian or some sort of noise prior latent distribution, wanted to somehow end up generating some samples from the distribution by designing a generator who is able to convert a noise sample into a sample from more data distribution. We discussed that this is not possible to do it directly. Uh, because we could not really do maximum likelihood estimation anymore. There was no inversion happening in this kind of generator. And given that we don't have the reverse model, we cannot really write down maximum likelihood estimation explicitly. And this was the reason that we developed the alternative approach, which was the min-max gain, right? And then the min-max gain somehow concluded that to be implicit form of maximum likelihood. Essentially, when we were solving that min-max game, we were essentially finding the minimum, or we were minimizing the Jensen-Shannon distance between two distribution, the distribution of the generator and the data distribution. And we concluded this is a somehow implicit maximum likelihood estimation, which makes sense because maximum likelihood is the ultimate thing we want to do when we are trying to uh, train a model. But we ended up this discussion that this idea we had is what we call it vanilla GAN for the given particular given um, mm, loss function that we are minimizing or solving the min-max problem. And there are a bunch of issues with this vanilla GAN. The main one is the training instability. So the gradient descent algorithm that we are using needs to get the gradients of those, minimization and maximization inside of the objective gradient. And we talked about it that those gradients are not perfect, and because of that, we get into troubles. So it's going to be very sensitive to the hyperparameter tuning when we are training such models, and this is one of the roots of instability. So we can simply, by changing tiny bit of hyperparameter or a tiny change in the training algorithm loop, it could happen that this is immediately diverging. So mode collapse, this is one other issue. We discussed this. So this is one of the big issues they have. The generator at some point starts to somehow generate good samples, and those samples are going to be classified by the discriminator to be the real sample. So this means that generator is successfully fooling the discriminator. Because of that, we are lacking diversity. Meaning that the generator keeps on generating the same samples over and over, or a bunch of few samples, because this is going to be always classified as real, so it's going to get good feedback. But then when we use that GAN model to sample new images, for instance, or new samples from data distribution, we are most of the time getting those few samples, and this is lacking the diversity, right? This is what we call it mode collapse, and this could easily happen in vanilla again when we do it with basic training loop. And another issue is the one which we discussed last time. So they are quite vulnerable to vanishing gradient. And because of that, um, we need to come up with some tricks to get rid of that vanishing gradient. All of these together somehow motivated many people to think out of the box and see whether they can come up with an alternative solution for GAN training or training an architecture of adversarial form. And they ended up with the idea of Wasserstein GAN, which is the topic that we are going to discuss today. So here, one particular hint or particular note that we should give here is that we eventually have two sort of like W-GAN and vanilla GAN, but they are not different in their architecture. So it doesn't mean that W-GAN is an alternative architecture or generation approach as compared to vanilla GAN. Now, both of them are GAN, and GAN essentially is just a generative adversarial network consisting of uh, generator and discriminator. So W-GAN and GAN, both of them are the same architecture. The only difference is that in W-GAN, we take an alternative approach to train that. So we don't simply look at the vanilla min-max game, or we do not just develop that um, intuitive training algorithm. Instead, we just use alternative approach. So this is very important to pay attention to this, that despite very tiny changes that we might give to the architecture, given that W-GAN gives us some other, you know, um, alternative assumptions on these modules, but at the end of the day, we always have a GAN. So GAN is always the same thing. W-GAN, Wasserstein GAN, is simply an alternative approach to train them. Now, let's focus on GAN once again. So the idea in GAN is that we have one latent space, typically Gaussian. So this is where we sample a latent variable, a Gaussian noise, then we pass it through a generator. It's going to give us one sample. This is the model sample X. Then we're going to give it to the discriminator. You're going to discuss whether this guy is real or fake, right? This was the vanilla form. But if we want to think more general, then we could say that once we get this X, we're going to give it into a discriminator block. And this is going to give us some output, Y, which in the vanilla form is essentially the classification output for this X being real or fake. But in general, it can be some output, which is going to give us some sort of information we can compute a risk with. Once we have the risk, we can train both of these two architectures, the generator and discriminator together. So this is a general idea of GAN, and it's the case for every form of GAN that we have. Now, in the vanilla form, the main thing that we were computing here, so this output Y was the output of a classification problem, and then we had this risk. Now, what we should do with this risk, we just do the min-max problem again, right? So we maximize the negative likelihood. Sorry, we maximize the likelihood itself to make sure that we are doing the best discrimination, but at the output, look, we do the minimization to somehow make sure that the generator is full, the discriminator. But we said that this implicitly means that we are maximizing the likelihood of the generation. Or in other words, we are minimizing the Jensen-Shannon divergence. So this output Y is going to help us to compute some estimate of this Jensen-Shannon divergence. And using that estimate, we try to minimize this divergence, which ends up to be the vanilla GAN. So we can look at the problem this way. Now, the alternative form is to use what we call it Wasserstein GAN. I am going to break it down for you what exactly this Wasserstein means. But if I want to just give you a very high-level description of the process here, is that we get this Y, and out of this Y, we compute some risk which is going to be somehow proportional to the Wasserstein distance between the output or the distribution of the output of this generator and the data distribution. And you might ask me, what is Wasserstein distance? How we can estimate it, and why we should minimize it? Is there any reason for that? I'm going to explain it all of it together. So there is no worries in that respect. So I don't consider any background on this here. But the point that I want to just give you the big picture here is that this y is going, the output of this discriminator could also help us estimate the Wasserstein distance between the model and data distribution. And then we try to minimize it by, again, just coming up with one training loop. So this is the idea. And now let's start to break down the components of this idea, which ends up being Wasserstein GAN. So to understand the Wasserstein GAN approach, we need a bunch of definitions, as I also mentioned in the lecture to the students. So it doesn't mean that you need to have a very concrete understanding of these stuff, but given that every text on this topic is including these notions, I think that they are really necessary. Just that you understand what those notions are. So the first thing is the idea of coupling set. And what does it mean? The idea of coupling set is simply a kind of mathematical definition to define a kind of set of distributions which are valid marginally. So what does it mean? Let's think of two distributions, say P and P hat, both of them are distribution on the same data space X. It means that they are two different distributions defined for the same kind of random variable. For example, two binary distributions. One of them has probability half-half, the other one has the probabilities 0.3, 0.7, right? They're both distributions defined on a binary random variable. This data space is simply 0 and 1, but they are somehow having different values, right? They're still different distributions. Now, when we have two distributions, we can think of two random variables who are jointly distributed, and each of these distributions are giving the marginal distribution. But the joint distribution is not unique anymore because we don't know the joint, we only know the marginal distributions, right? Now, we can define something we call a coupling set of these two distributions. And these two distributions are essential. This set is defining the set of all joint distributions where the marginal distributions are exactly the same as what we have, but the joint distribution could be anything, right? So if you look at the definition, now the coupling set is defined for P and P hat. So just remember the binary distributions. One of them is half-half, the other one is 0.3, 0.7. And then it is the set of all joint distribution. It means that now we have a joint distribution for two binary variables. So it's going to be a table of 4 different values. And this table here, you have marginal distribution on X to be something specific, P. This is the first distribution we have. So we want, when we are marginalizing over X hat, the second random variable, we end up with a half-half distribution. And when we are marginalizing over X, we end up with the distribution of X hat, the P hat distribution, 0.3, 0.7 in our example, right? But we don't care about the joint distribution. So any joint distribution that has this property is one of the possible coupling distributions, and we take a set of them. So eventually this set could be for, like, if you would think of a general data space, it could be a very huge space, right? Now, defining this guy here, now, if we want to think intuitively about this set, it's essentially thinking of any joint distribution that is describing those marginal distributions, as I said. And this guy somehow include those joint distributions, which are having no correlation at all. So it's not hard to see that if you think of Q, like the joint distribution, be the independent distribution of X and X hat. It means that P and P hat are multiplied, right? So if you multiply them, this is still a joint distribution. In this case, X and X hat are independent. And you're going to see that, it's obvious that this Q is going to satisfy this condition here, right? So this independent distribution is going to be definitely one of the guys inside the set, right? The set is never empty. but you could have also lots of other joint distribution, and some of them could be extremely correlated, right? For instance, you can, under some circumstance, like in particular examples, you can think of the case where you have exactly the same random variable and copy it, like X hat is a copy of X exactly. And then marginally they're distributed the same, but the joint distribution is not independent anymore because once X is changed, X hat is changed exactly the same, right? So you can think of different data spaces, and for each of them, you can come up with tons of examples where you have a joint distribution with the same marginals, and all of them are included in this distribution. So moral of the story, some of joint distribution Q in this set are extremely correlated. Some of them are, I mean, at least one of them is totally independent, right? And some of them have like small correlations, right? Now, having this said, define, now we can define what we call a Wasserstein distance. And the word Wasserstein comes after the name of a mathematician who initially somehow worked with this kind of distance measure. Now, what is this distance? I mean, you don't really need to think of distance. I mean, for those who think of mathematical definitions, you can again think as a divergence. So if you remember, we had Kale divergence, we had Jensen-Shannon divergence, and all of them were a kind of metrics which were talking about looking at two distributions, say P and P hat, and tell us how different they are. So when these divergence values are big, then this means that those distributions are totally different, and they are not a good thing when we are thinking of P hat approximating P. But when the value is very close to zero, then this means that eventually p hat is same as p, right? And this means that p hat is a good estimate of p. We are interested in such definition always in this generative AI setting, because eventually the whole purpose is that we develop a kind of model which can come up with a sort of p hat which is very close to original p, the data distribution. Now, Wasserstein distance is another form of distance or divergence, say, that is computing the difference between p and p hat. Now, say I have p and p hat, and say they are both defined on the same uh, data space X, so they are essentially two distributions for the same thing. Now, I want to know how different they are, right? So what I can do, I can make this p the coupling set, right? So if I have this pi set, pi of p and p hat, this is going to include all possible joint distributions Q whose marginals are p and p hat, right? Now, I'll look at this every single Q inside the set. And now when I fix Q, I have the joint distribution. Now I can think of X and X hat to be distributed with this joint distribution. And I compute the difference, exactly the Euclidean distance between these two. So if I compute this expected Euclidean distance, this expected difference between X and X hat with respect to Q, I'm going to end up integrating out X and X hat, and I end up with one value which only depends on the choice of Q, right? So this whole expectation is going to change only when I change Q. Now, if I could access all the distribution inside this coupling set, which you might think is a very hard thing, and you're totally right in that sense, we're going to get rid of this challenge later. But if I can find out all Q distributions which are inside the coupling set, now, and I compute this distance, Euclidean distance, average Euclidean distance for every single of them, then the one which is minimum value is going to give me the Wasserstein distance. Now, this is a bit of too much math. Now we can think a bit intuitively about this. So it's essentially, we can think that Wasserstein distance looking at all possible cases that X and X hat are distributed as we see, like X is distributed with P, X hat is distributed by P hat. Well, we know that there are lots of cases where this happens. Some of them are the case where X and X hat are extremely correlated. Some of them are the case where X and X hat are totally not correlated. Now, For every single of them, it somehow finds what is the average distance between x and x themselves, right? So it's going to say if x is distributed with p and x is distributed by p hat, when we have extremely correlated case, we have this distance, and when we have like totally uncorrelated, we have this distance, right? And then it's basically goes and find the takes the distance which is minimum, or in other words, is somehow optimist in that sense. And you're gonna say, let's say assume that x and x are the most correlated form ever, right? And then what is their distance? This is the distance that they could minimum have, right? And this is what we take it as a kind of Wasserstein distance. So this is somehow intuitive definition of Wasserstein distance, but as we're going to see, we're going to get rid of this, more complicated mathematical form, and we get into more easier form in a couple of slides. Now, you might ask me what is special about this Wasserstein distance that we want to use this. So the whole idea that we want to do before I just jump into the details is that instead of doing implicit minimization of Jensen-Shannon distance as we did last time with vanilla GAN, we want to replace the JS divergence with this Wasserstein distance. You might say, what is special about this guy? Okay, the idea is that this guy is quite smooth and it's going to help us do the minimization more efficiently. So just let me give you one example. And this example is the one which is given in the original Wasserstein GAN paper, the original one. And it's a very intuitive example explaining the whole idea. So let's think of a very basic case where we have latent variable z. So this is a dummy example where I have a latent variable z, which is uniformly distributed between 0 and 1. So it could be with probability 1, sorry, not probability, with density 1, it could be any number between 0 and 1. Now, it's distributed uniformly on this set, and what we know is that the original data, so this is a kind of, geneated information that I have, that the exact data is made by putting this latent as the second entry and letting the first entry to be 0, right? So the latent variable is one-dimensional, the data is two-dimensional, but this is, even though it's a two-dimensional vector, it's going to always be on the line where the first entry is 1. So if I think of x to be x1, x2, it's going to lie on the line x1 equal by 0 in the 2D space. So this is what we talked before about. The data is lying on a one-dimensional manifold of a two-dimensional space. And what I can say that I know this fact that the data is low dimensional, right? Now, assume that I want to somehow make a train a generator which can generate one sample x hat for me. And this sample x hat, I am trying my best to somehow look like the data sample x, right? So the point is that when I'm doing the generation, I eventually don't have access to this information that X is available at 0 and 0, but I have access to latent. This is the story that we have in most generative models. We have some, we somehow develop some information on the latent space, which is low dimensional space, but we don't exactly have the idea about the data space, right? So I don't have this information because if I have this, the whole problem is over. So I don't need to do anything by 0, anything anymore. I just put it 0 and z and everything is over, but I have access to z. Now, the model that I'm training is in this form. So this is the generator that I have. My generator has only one parameter, theta, and this parameter theta is going to be the value of first entry. And I put the second entry to be z. So this is not hard for us to see that if I set theta to be 0, the output x hat is going to be exactly x. So it means that I am able to train this g. If I can come up with some good solution, I can somehow end up with one generator, which is exactly sampling from my data distribution. So everything perfect here. Now, the point is that I yet do not know what is the exact value of theta, and I need definitely come up with some, loss function and try to minimize it, right? Like whatever we have done up to this point. And I am assuming this guy to be a theta, and I just let theta to be between minus 1 and 1, and I just try to find the optimal value. Now, let's say that I go on to do that. At the end of the day, I need to somehow find a kind of distance between the distribution of this x hat and the original data distribution of x, and I try to minimize it, right? So that it's going to get 0, and then this means that now x hat is exactly looking like x, right? Now, in that sense, I have different choices for divergence to compute the divergence between distribution of x hat and x. And let's look at the three main candidates, the KL divergence, the JS distance, and also the Wasserstein distance, the three guys that we have learned up to this point. Now, let's set out the problem together. So I have x hat, which is in this form, theta and z. And z is my latent variable, which is uniform on the set 0 and 1. And my data distribution is going to, of course, be in this form, right? Because my x hat is going to be one value here, which is theta. That guy could be between minus 1 and 1. And then the second guy, z, is uniformly distributed between 0 and 1, so it could be anything between 0 and 1. So this is the space that I'm going to search over to find my best distribution, right? So this is the only set that any sample that I have out of my generator is going to be one point in this set. No way it can get out of it. So this is my data space. Great. Now, the next thing that I need to do is to just find out what is the exact data distribution. And just as a side note, just as a reminder, we don't think that in practice we do not have access to the data distribution, of course. But here, the thing that we are trying to do is that we just want to see how these distances are going to look like, right? So it doesn't mean that I have I assume that I have the distribution in practice is just to specify what the distribution is, like a geniated information. Now, data distribution is happening exactly at line x1 equal by 0. So I do know that x1 should be definitely 0, but x2 could be uniformly distributed, right? Between 0 and 1, that is the data space. So it means that at point x1 equal by 0, I'm going to see the impulse. Anywhere else, it's going to be 1, right? And this is going to be data distribution. So if you find it a bit like new to you, it's not hard to try playing around with it, and you're going to see it immediately once you just do a bit of investigation on that. So we did it in the lecture. So we tried to just integrate it over the data space. It was 1. Then everywhere it is going to be 0. Not negative. And because of that, we concluded this is a joint distribution. Now, one thing that you should pay attention that this guy is Dirac impulse at point 0. And if you do not remind the definition, maybe you can just stop here and take a look at definition of Dirac impulse to get a kind of understanding about that. But it simply means they're gonna get a spike at point 0, which is asymptotically going to infinity, and it's going to be 0 anywhere else. And it has this property that when you take the integral from anywhere on any set, which includes that point 0, it's going to be 1. So that is the data distribution. Now, the distribution at the output of the model is going to essentially be the same kind of distribution, but at the line theta, which is the model parameter, right? So this is going to be p hat of theta. This is our model, and this is the distribution. Again, it's not hard for you to just check the conditions for a joint distribution. You're going to see that they are all satisfied, and this is perfectly matching the model distribution. Now, this is a Dirac impulse at point x1 equal by theta. And the point is that I want to find out what is the distance between these two for different values of theta. And hopefully when theta is minimized, when I minimize the distance with respect to theta, I'm going to end up with theta equal by zero, which is the true value for theta given the data distribution. Now, let's start with the KL divergence. So if I want to compute the KL divergence between P and P hat theta, I just need to write down the definition. So just as a reminder, expectation is taken with respect to P. It's the guy which is showing up in the denominator, and then the denominator is going to be the second distribution, right? And doing so, now we can just open it up, right? So the expectation in this case is simply an integral. So the integral is over the whole data set. So x1 could be anything between -1 and 1. x2 could be anything between 0 and 1. So it's going to be the integral dx1 dx2. So that's it. And now inside the bracket, I'm going to have log of p divided by p hat, as you can see. And then here, I'm going to multiply everything with p. Now, this kind of integral is a bit spatial, I would say. So it's not a very, convenient analytic function inside the integral to do the calculation. So you might need to review a bit the Dirac impulse definition, but I'm going to give you a brief idea how we can take this integral. If we want to take an integral of any function multiplied by Dirac, then eventually the thing that we should do is to see the Dirac is happening at which point. And we're going to take that point, we calculate the function at that point, and we take it out of the integral. So this is the typical way that we do it. So essentially what we need to do, we should see what's going to happen to this log expression at x1 equal by 0. And then we get rid of the first integral log of that term at point 0. Now, the point is that this log is eventually not again well-defined because it's in terms of Dirac impulse, but it's not hard to see that when for different values of theta what going to happen. So let's do it together. First, let's put theta equal by 0. If theta equals by 0, then this denominator and denominator are going to cancel out. Again, I do know they are spatial functions, but we can show that when we put it inside the definition, that limit exists, and this is going to be 1. So that happening, this means that I'm going to have log 1 coming out of this integral. This inner integral over x1 is going to just get to be 1. And then the second integral is only remained, right? So it's going to be log of 1 integral over with respect to dx2. Again, this guy does not depend on x2. It's going to come out. The integral is 1, but log of 1 itself is 0, right? So this KL divergence is going to be 0. This is what we expected, right? Because at theta equal by 0, x and x are exactly the same thing. Their distribution is the same thing, and the KL distance between them should be 0. So this is not wondering. Now, what if we have theta not 0? So if we have theta not 0, then this means that I'm going to have this guy, right? And I'm going to have this guy, and at point 0, which I need to have because of this impulse here, so at point x1 equal by 0, this guy is, of course, the spike, the one which is going to infinity, right? But this other guy is the one which is like almost 0, right? Either almost exactly 0 or almost 0, right? So this means that this term is eventually not really defined. But if we just take a bit of, simplification, so we don't, we just do a bit of, slight relaxation to this analysis, we could say this is a big number, say infinity, divided by a very small number, which is almost 0, and then big divided by 0 is essentially big, right? So it's going to be infinite. It's going to go to infinity. And it's going to go to plus infinity because this guy is eventually a plus sign big number, right? So what we can say this is eventually almost zero everywhere around zero, which is the place where we are computing the integral. And because of this, this whole log term is going to infinity, right? So I'm going to have integral of infinity, and I mean that infinity is going to remain infinity no matter what the integral is, right? So moral of the story, when theta is not zero, this scale divergence is eventually infinity, right? So what I can say the scale divergence, if theta is zero, it means that exactly I am mimicking the data distribution. It's going to be zero. This is what we expect. And anywhere else it's going to be plus infinity, right? So this is what we expected, the data distribution, when it is exactly same as the model distribution, this scale divergence is going to be minimized, but in the other cases, it's going to be something positive. But there is one point that we should pay attention. This positive value that we have for KL, so assuming this is the scale divergence that we have here. So this point here, as you see, at point zero, it's going to be zero, but anywhere else, it's going to be plus infinity, so something more than zero. But that something more than zero is eventually mathematically not defined, right? Because so there's going to be a kind of limiting expression divided by zero, which cannot be defined, right? So we can somehow intuitively say that this is going to be plus infinity value, right? Extremely large value. Now, this is what's going to happen to the KL divergence. Now, what's going to happen to the Jensen-Shannon divergence? So we defined Jensen-Shannon in the previous lecture, and this is looking like this guy. So it's the KL between A and the average, P and average distribution, plus KL between P hat and the average distribution, right? So the both distributions. And P and P hat here are the data and the model distribution, right? And the average distribution is eventually defined as the data distribution plus the model distribution divided by 2. So this is how we define the JS divergence. Now, here our data distribution is impulse, the model distribution is impulse as well, so we're going to put it in the definition, and then we try to just compute the JS divergence. Now, let's start with the first term in this expression. So we have two KL divergences. We need to just compute them. We already did one KL divergence computation, so we can easily extend that idea here to compute each of them. So let's start with the first term. And for the first term, let's set theta again to 0. So when theta is 0, this means I have delta plus delta, right? So I'm going to have 2 delta the same, and then going to be 2 delta divided by 2. So this average distribution is going to be exactly delta, data distribution, right? So I'm going to have data distribution here, P, and then here I have P, so KL should be 0, right? This is what we expect, and it's not hard to see it here, right? When I put this average distribution in the denominator, so I'm going to have delta x1, this is the data distribution. Delta x1 again, this is the model distribution because theta is 0, so there is no theta here anymore. Divided by 2, that 2 is going to the denominator. Now I have 2 delta divided by 2 delta. This is going to be 1. And then we can just argue as before, so it's going to be 0, right? So when theta is 0, this first scale divergence is going to be 0. You can easily see that the second one is also 0 as well, because in this case, P hat, P, and the average, all three are exactly delta x1, right? So this is going to be 0 as well. Now, when theta is not 0, let's look at the first expression. So it's going to be P and the average distribution. So I'm going to put P here in denominator, right? And the average is going to be delta x1 plus delta x1 minus theta. This is the model distribution divided by 2. And I immediately take 2 to the denominator. So I'm going to get rid of this. So I'm going to have this guy, right? Now, when theta is not 0, this means that this guy is going to be something non-zero. And something non-zero is eventually that very big spike number, right? That somehow like plus infinity. Now, this guy, when I am taking the integral, Uh, and this is happening here at point theta, right? This other guy here is going to be that very big number, that plot, very large plus number, plus infinity, we can say, at point zero, right? Now, the integral that we want to take is between minus and 1 and 1, but given that we have delta here, we only care about the value around 0, right? And around 0, this guy is eventually 0, but this guy is exactly the big number that we have in the denominator, right? And they are going to cancel out. Given that this is happening, so we're going to end up with log of 2 only coming out of the integral. So we can write it down to be a log 2. And this log 2 is going inside the second integral, the outer integral over x2. But this is a constant. It's coming out, right? And the integral over x2 is going to remain 1, right? And because of that, the whole integral going to end being log 2, right? So moral of the story, when theta is not 0, we have log 2 as the output of this integral. This is different to the KL case, where we ended up having plus infinity, right? Because we had only this term in the denominator, and this is the one which is ruining everything. Now, what we can say that the KL divergence between P and P hat, both of them, they are going to be log 2 when theta is not 0. It's going to be 0 when theta is 0. Now, we computed everything here for P. It's not hard to see the exact same thing happens when you have P hat. And because of that, this is going to be the case for both expressions in the definition of JS distance. Now, putting them together, then the JS distance is going to be eventually this guy, right? So it's going to be 2 times log 2 when theta is not 0. It's going to be 0 when theta is 0. One thing, in the original paper, when you read it, you're going to see that there is no 2 here, because there they define JS distance or JS divergence to be KLPA and KLP hat A divided by 2. So they average those two KL values. But we didn't do this in our definition, so this is why this 2 shows up here, but it doesn't change anything. So it's a very minor. Now, one thing again that we can see here is that this JS distance is eventually getting 0. And when theta is 0, which means that when P and P hat are the same, this is again the thing that we expected, because we know that the JS must be 0 when we have two same distributions. But the point here is that now when we plot this guy, we eventually have the values out of the point theta equal by 0, which are now defined. So they are defined. They are not plus infinity anymore as in KL, but they still have a bad property, and that is that they do not have any gradient. So it's true that they are zero, this is defined everywhere, but if I want to really minimize this guy with respect to theta, I need to compute the gradient, or here derivative with respect to theta, and eventually the derivative anywhere here or here is 0, right? So there exists no derivative. The algorithms are not going to work and are not going to help us end up with this solution, this point here, right? So this is an issue when it comes to the computational models which we have in practice, because all of them work based on gradient. So JS is doing better than KL in the sense that it is able to define the distance, but it's still not giving us what we want because it does not give us any gradient. Now, let us compute the Wasserstein distance, and you might tell me, okay, Wasserstein distance was too complicated to compute, but a good thing about this example is that in this particular example, you can easily compute it. So I need to think about the coupling sets, right? And then for every joint distribution inside this coupling set, I compute this guy, right? And then I try to minimize it. That's right. But the point here is that I really do not need to know this couple distribution. Let's say that I'm thinking about x and x hat. So x is 0 and z, x hat is theta and z. The Euclidean distance between these two is going to simply be absolute value of theta. And pay attention, this is absolute value, not theta itself, because theta could be also negative, right? And then when you find the distance between these two, it's going to be absolute value of theta. Now, this absolute value of theta does not depend on x nor x hat. And because of this, when I take this expectation, regardless of what this distribution is, this guy is going to always be theta, right? So here, this expression is always going to be absolute value of theta. And if I want to minimize it, since it does not depend on Q, the minimum is also the same thing, right? So moral of the story, the Wasserstein distance between P and P hat in this case is absolute value of theta, right? And again, it's very easy to see that this guy is going to be minimized when P equals by P hat. When P equals by P hat, theta is 0. And when I put it 0, this is 0. This is the minimum value this absolute value could have. So Wasserstein distance, same as JS and KL divergences, is going to be minimized at the exact point where P and P hat are the same. But there is one key difference here. The key difference here is that this guy now has very good gradients, right? So this absolute value of theta is a kind of function I can easily minimize by numerical algorithms, right? And this is the whole reason that we are interested in the Wasserstein distance. So if we want to think about how these three different guys look like, so KL divergence is going to be this red curve, right? Here, the lines that you see red, even though we are showing it, they are not really defined. So computational thinking about them, they are plus infinity, like they are always overflowing your computer. Whereas the JS is going to be defined, so that is like a finite value, but the point is that it does not have any gradient, meaning that if I start with some theta non-zero, and I want to just compute a gradient with respect to theta such that I update theta and I gradually end up with the value 0, I'm not going to get any gradient. I'm going to stay there forever, right? And this is not something good in practice because we want to use gradient for minimization at the end. But this guy is the Wasserstein distance, which is now very well defined. It's going to show the same property. It's minimized at the point that we want. But the key point is that at any point that I start, if I start here, for instance, then whatever theta is, I'm going to always get a gradient which is pushing me towards the point 0. Or if I start here, again, I'm going to get a gradient in this direction, which is pushing me towards 0, right? So this guy is now having gradient is something useful, right? And this is the main conclusion behind that led to the definition of Wasserstein GAN. So the key observation they had based on this example and other, mathematical investigations was that even though all of these metrics are going to be minimized at the point that we want, but KL is not defined, it's not a kind of good thing. So it's very hard to minimize it in practice. And this means that I can only get KL0 when I'm exactly on the data manifold. If I'm out of that, I cannot even define it. Same thing pretty much happens with JS. I only get it minimized at the data manifold. Anywhere else, it's not undefined, but it's not having any gradient, which can push me towards the data manifold. But Wasserstein is somehow very well defined everywhere. It has gradient everywhere, and then it can eventually push me towards fitting into the data manifold, right? And this is the moral of story. So minimizing Wasserstein distance is somehow looking like a more stable and practical approach as compared to minimizing KL divergence or Jensen-Shannon distance in this particular case.